Space-time might be just the surface of a much deeper reality. Beneath everything we perceive could lie a quantum fabric, the universe's true operating system. This hidden code dictates the behavior of galaxies, the flow of time, and the existence of matter itself. By the end of this journey, you will understand the universe not as a stage, but as a dynamic, computational process. We will uncover how the smooth continuity of space could be an illusion emerging from discrete quantum bits. We will question what truly happens at the heart of a black hole and how time itself might boot up from a more fundamental layer. Are you ready to explore the source code of existence? This seamless reality we move through could be an exquisite illusion. The idea of a quantum fabric suggests that space and time are not the bedrock of existence, but rather a secondary effect, a kind of emergent property. It is a theoretical framework born from a deep conflict in physics. On one hand, we have Einstein's general relativity, which masterfully describes the grand cosmic dance of gravity and the warping of space-time. On the other, we have quantum mechanics, which governs the bizarre, probabilistic world of the very small. These two theories are brilliant, yet they speak different languages and refuse to be merged into one. The quantum fabric is the proposed solution, a more fundamental layer from which both could emerge. Imagine the screen you are watching this on. It appears to show a smooth, continuous image, but you know it is actually built from millions of individual pixels, each one a tiny, distinct point of light. Now apply that idea to the cosmos. The seemingly smooth, continuous fabric of space-time might be composed of unimaginably small, discrete quantum units. This is the concept of atoms of space, where space itself is not infinitely divisible but comes in tiny, indivisible packets. Pioneering physicists like Smolin and Carlo, Rovelli explore this through a theory called loop quantum gravity. It proposes that space is not a void but is woven together from finite, interconnected loops of gravitational field. Think of it as a cosmic tapestry, where each thread is a fundamental loop of information, and their interconnections create the geometry of space we experience. This quantum substrate would have properties utterly alien to our classical understanding. It would be granular, not smooth, and its very structure would be governed by quantum probabilities. Understanding this definition is like learning the alphabet before you can read the code. It is the first, crucial step in decoding the universe's true operating system, forcing us to ask how this intricate fabric is woven together in the first place. Isaac Newton envisioned the universe as a grand, immutable stage. Space was an absolute, unchanging container, and time was a universal river flowing at the same steady rate for everyone. This classical view provided a solid foundation for centuries, a predictable backdrop against which the cosmos performed. But that stage was destined to be broken apart. Albert Einstein stepped forward and revealed that space and time are not passive. They are dynamic, interwoven into a single fabric called space-time, a fabric that curves and stretches under the influence of mass and energy. A planet does not orbit the sun because of a mysterious force. It simply follows the curve that the sun's mass creates in the cosmic cloth. This was a breathtaking leap in understanding, transforming our view of the universe from a static scene to a dynamic, interactive entity. Yet for all its power, Einstein's beautiful theory has a fundamental limitation. It describes the cosmos perfectly on large scales, but it falls completely silent when faced with the bizarre rules of the quantum world. Quantum mechanics governs the realm of the incredibly small, where particles can be in two places at once and reality is a game of probabilities. These two pillars of modern physics are both spectacularly successful in their own domains, but they are utterly incompatible. You cannot apply the equations of general relativity to the heart of a black hole or the first moments of the Big Bang without them producing nonsense, infinities that signal a complete breakdown of our understanding. This glaring conflict forced physicists to search for a deeper theory, one that could unite the cosmos of the very large with the quantum of the very small. Visionaries like John Wheeler began to speculate, proposing that at the tiniest possible scale, the smooth fabric of space-time might not be smooth at all. Instead, it would be a chaotic, bubbling foam, constantly fluctuating with wild energy. This concept of quantum foam hinted that space-time itself has a discrete, granular structure if you look closely enough. The historical journey from Newton's absolute stage to Einstein's flexible fabric, and now to the possibility of a quantum foam, shows a clear progression. Our understanding has evolved from seeing space and time as a passive background to an active participant, and now to a property that might emerge from something even more fundamental. This context makes the quantum fabric hypothesis not a wild guess, but the next logical, if profound, step in our quest to decode reality. So what mathematical language can we use to describe this hidden quantum world? Loop quantum gravity offers one of the most tangible maps to this hidden quantum world. It proposes a universe where space itself is not a smooth, empty void, but a dynamic fabric woven from an unimaginably dense network of tiny, vibrating loops. These are not loops of any material substance, but fundamental one-dimensional threads of pure gravitational field, woven together into what physicists call a spin network. Picture a cosmic chainmail vest, where each interlocking link is a discrete, quantized packet of space. Each loop in this network carries a specific, quantized amount of area, and the way they connect defines a fundamental unit of volume. This means space is not infinitely divisible. You cannot keep cutting it into smaller and smaller pieces forever. There is a fundamental limit, a smallest possible size, much like a digital image has a smallest unit, a pixel. This is the core of loop quantum gravity, a theory largely pioneered by physicists like Abhay Ashtekar, Lee Smolin, and Carlo Rovelli. Its power lies in its background independence. Unlike other theories that assume space-time is a pre-existing stage, LQG builds the stage itself from the relationships between these loops. There is no container without the contents. The theory then asks how this frozen, static network of space evolves. The answer lies in a fascinating concept called spin foam. If a spin network is a single snapshot of space, then a spin foam is the entire history of that space, a complex, frothing structure that charts how the network changes and evolves over time. Imagine a time lapse of a growing crystal, with new connections constantly forming and dissolving. This four-dimensional foam is the theory's description of space-time itself, a seamless blend of the three dimensions of space with the one dimension of time, all emerging from these quantum relationships. The smooth, continuous reality we perceive is therefore a grand illusion, a collective effect of trillions upon trillions of these discrete quantum interactions. Much like a movie appears continuous though it is made of individual frames. This framework provides a compelling, if mathematically complex, vision of a discrete universe, one where the very geometry of reality is written in a quantum code. Yet, this is not the only candidate for the universe's source code. A radically different approach emerges from the world of theoretical strings. String theory presents a radically different vision for the universe's source code. It suggests the most fundamental ingredients of reality are not zero-dimensional points but incredibly tiny, vibrating loops of energy. The specific vibrational pattern of each string determines its identity, creating the diverse cast of particles that make up our world from quarks to photons. One note might produce an electron, while a different harmonic creates a graviton, the hypothetical carrier of gravity. This elegant idea, however, requires a grander stage than we perceive. For the math to work, these strings must dance through a space of 10 or even more dimensions, with all but the familiar 3 of space and 1 of time curled up into sizes too small for us to detect. From this framework emerges one of the most mind-bending concepts in all of physics, the holographic principle. First proposed by Gerard T. Hooft and later developed by Leonard Susskind, this principle suggests that all the information describing everything within a volume of space can be completely encoded on its boundary surface. Think of a common hologram like the one on your credit card. A flat, two-dimensional surface holds all the data needed to project a full, three-dimensional image. The holographic principle argues our universe might operate on the same cosmic scale. The three-dimensional reality we experience, with its stars, planets, and people, could be a magnificent projection. The true quantum code, the universe's operating system, might be written on the distant, two-dimensional surface of the cosmological horizon, the ultimate boundary of our observable universe. In this view, space-time and the force of gravity are not fundamental at all. They are collective, emergent phenomena, like the wetness of water emerging from countless individual molecules. They arise from the complex quantum interactions happening on that far-off two-dimensional screen. This framework radically redefines existence, proposing that we live inside a cosmic hologram, a projection of information. It compels us to ask a deeper question. If reality is a projection of information, what is the nature of that information, and what are the fundamental bits that store the code of the cosmos? So if reality is a projection, what exactly is being projected? The answer may be simpler and more profound than we ever suspected: information itself. The legendary physicist John Archibald Wheeler captured this idea in his famous phrase, "it from bit." He proposed that everything in the universe, every particle, every force field, and even the fabric of space-time itself, ultimately emerges from binary answers to yes or no questions. These are the universe's fundamental bits. In this view, what we perceive as physical reality is not the foundation. It is a secondary manifestation, a consequence of an underlying layer of pure information. The quantum fabric is not just a tapestry of energy, it is a computational substrate processing these bits according to cosmic rules. This perspective, often called digital physics, sees the entire cosmos as a vast and likely quantum computer. The evidence for this is not just philosophical. We see it in the most extreme environments in the universe, black holes. The work of Jacob Bekenstein and Stephen Hawking revealed that a black hole's entropy, which is a direct measure of its information content, is not proportional to its volume, but to the area of its event horizon. This was a revolutionary clue. It suggests that all the information needed to describe everything that ever fell into a black hole is somehow encoded on its two-dimensional surface. This discovery is a direct pillar supporting the holographic principle, powerfully reinforcing that information is not just stored in the universe, but that information is primary, and the physical universe is its expression. What does this truly mean for the nature of reality? It implies that the laws of physics we work so hard to uncover are not the bedrock. They are the software, the algorithms running on the universal quantum hardware. Gravity, electromagnetism, even the passage of time, are not fundamental forces but emergent properties of this cosmic computation. This informational perspective forces a complete reconsideration of existence. If the universe is a processing system of data, then what is the nature of the processor and what ultimate program is it running? This spooky action at a distance might be the universe's fundamental binding agent. Quantum entanglement is a phenomenon so strange it seems to defy the very concept of separation. When two particles become entangled, they lose their individual identities, forming a single, unified quantum system. Measure the property of one, like its spin or polarization, and you instantly know the state of its partner, even if that partner is now on the other side of the galaxy. There is no signal traveling through space, no exchange of energy. It is a correlation that transcends space and time, a connection that operates on a level deeper than the physical realm we perceive. Albert Einstein was deeply troubled by this, calling it spooky action at a distance because it seemed to violate the cosmic speed limit set by light. Yet, decades of meticulous experiments have confirmed its reality. Scientists can now create entangled pairs of photons or atoms and show that their fates are linked in this instantaneous, inexplicable way. But what if this is more than just a bizarre quantum quirk? What if entanglement is the cosmic thread that weaves the quantum fabric into a coherent whole? A revolutionary idea called the ER Equals EPR Conjecture gives this a breathtaking geometric form. It proposes that two entangled particles are not just mysteriously linked, they are physically connected by a microscopic wormhole, a bridge through the fabric of space-time itself. In this view, every single quantum entanglement is a tiny stitch in the cosmic tapestry, a fundamental bridge that literally constructs the geometry of space. The vast, complex network of these entangled connections could be what creates the smooth, continuous space we move through. Think of a vast, dark forest at night. Each entangled pair is like two people holding the ends of a long, invisible thread. Alone, they are isolated points, but as more and more people join, each holding their own threads and connecting to others, a vast, interconnected web forms in the darkness. You cannot see the threads, but they create a cohesive structure, a single network where a tug on one cord can be felt across the entire system. Our reality could be like that forest. The discrete quantum pixels of space, the loops in the spin network, are all bound together by countless threads of entanglement. From this impossibly dense, dynamic web of non-local connections, the illusion of a smooth, continuous, and local reality emerges. Entanglement is the hidden glue that binds the universe's quantum code into the consistent, predictable world we experience. It is the mechanism that allows the operating system to maintain coherence across the cosmos, making countless discrete quantum events appear to us as a single, flowing reality. The smooth space-time we navigate is a collective hallucination woven from countless quantum threads. This process is known as emergence. It is the same principle that explains how a gust of wind feels solid and continuous, even though it is just the combined motion of billions of individual air molecules. No single molecule is windy. No single molecule has a temperature. These are properties that only manifest from the whole. In exactly the same way, the seamless geometry of space and the steady flow of time might not be fundamental ingredients of the universe. They could be collective behaviors emerging from the frantic interactions of a deeper, discrete quantum layer. The mathematics behind this is profound. In loop quantum gravity, the smooth, three-dimensional space we perceive is not a given. It is a large-scale approximation of a buzzing, evolving network called a spin foam. Each tiny cell in this foam represents a quantum of space, and their collective connections build up geometry, much like countless individual stitches weaved together to form the smooth, continuous image on a tapestry. From our macroscopic viewpoint, we only see the final picture, not the countless individual threads. The holographic principle takes this even further. It suggests our entire three-dimensional universe, with all its rich content, is a projection from a two-dimensional quantum field residing on the cosmic horizon. The information for every star, every planet, and every person is encoded on that distant, flat surface. The emergence of our world from that lower dimensional code is a mathematical transformation, a cosmic rendering of a hologram. A crucial piece of this puzzle is entanglement entropy. This is a measure of the quantum entanglement between different parts of the system. Remarkably, physicists have discovered a direct mathematical link between this entanglement and the very geometry of space-time. The amount of entanglement between two regions dictates the spatial area that separates them. In this view, space itself is not the container for relationships, it is the relationship. It is the manifestation of the quantum information shared between fundamental elements. This realization forces a monumental paradigm shift. Space-time is not the fundamental stage upon which the drama of physics plays out. It is a derived phenomenon, a secondary effect that becomes relevant only at our large human scale. It is the universe's user interface, elegant and intuitive, hiding the impossibly complex quantum circuitry running beneath. If space and time are not fundamental, then what truly is? The answer may lie not in things but in the connections between them. An electron has no fixed position or spin until you measure it. This is not just a quirk of our imperfect tools, but a profound statement about the nature of reality itself. Carlo Rovelli's relational quantum mechanics pushes this idea to its logical extreme. In this view, the universe contains no absolute properties. Nothing has a state on its own. An electron's spin, a photon's polarization, even the location of a planet, only become real through interaction. A particle's properties are defined solely in relation to another object, whether that is a laboratory instrument, another particle, or you. This transforms our understanding of the quantum fabric. The fundamental stuff of the cosmos is not a collection of tiny, solitary things, but a vast, dynamic web of relationships. The universe is not made of substances, but of connections. This relational framework dissolves some of the most stubborn paradoxes of quantum theory. Take the famous thought experiment of Schrödinger's cat, simultaneously alive and dead. In a relational world, the cat is not in a ghostly superposition in absolute terms. It has a definite state relative to the radioactive atom inside the box, and a potentially different state relative to you, the observer, once you lift the lid. There is no single, universal reality, only a network of correlated perspectives. This fits perfectly with the idea of a universe built from information. Each interaction is a transaction, a simple exchange of a yes or a no, a single bit of data that defines a property in that specific relationship. The cosmic operating system is not processing isolated commands, but managing an unimaginably complex conversation between every part of the whole. Space-time itself may be the grand, emergent structure of this network. The distance between 2 points is not a primary fact, but a measure of the relational information, the number of quantum links or entanglements between them. We are all nodes in this cosmic web, our very existence defined by our connections to everything else. Nothing is an island. This deeply interconnected view forces us to look at the ultimate relational crucibles, the environments where space, time, and information are pushed to their absolute limits. Black holes are cosmic crucibles where the universe tests its own deepest laws. Nothing escapes their gravitational pull, not even light itself, creating a boundary in space known as the event horizon. This point of no return is more than a physical barrier. It is a frontier where our understanding of reality breaks down. the conflict between general relativity and quantum mechanics becomes an unavoidable crisis here. According to Einstein's theory, anything crossing the event horizon is lost forever, crushed into a singularity of infinite density. But quantum mechanics insists that information can never be truly destroyed. This is the infamous black hole information paradox, a puzzle that has challenged physicists for decades. If a book falls into a black hole, is the information printed on its pages erased from the cosmos? Stephen Hawking's own work revealed that black holes are not entirely black. They slowly leak a faint glow of radiation, now known as Hawking radiation, and over eons they can evaporate completely. This evaporation seems to suggest that the information about the book is irretrievably lost, violating a core tenet of quantum physics. The resolution to this paradox forces us to look at the event horizon not as a simple boundary, but as a dynamic component of the quantum fabric. The holographic principle offers a stunning solution. It proposes that all the information about everything that falls into the black hole is not lost inside. Instead, it is perfectly preserved, encoded on the two-dimensional surface of the event horizon. The three-dimensional interior we imagine is a projection from this vibrating, information-rich membrane. This is like a cosmic data storage device where the entire contents of the black hole are written on its skin. Loop quantum gravity provides a mathematical foundation for this idea. Calculations within this framework show that the entropy of a black hole, which is a direct measure of its information content, arises naturally from counting the possible quantum states of space on the horizon itself. Each discrete loop, each quantum of area, contributes a bit of data to this cosmic ledger. Black holes are not information shredders. They are the universe's most efficient information archivists. Studying these enigmatic objects gives us a direct window into the quantum structure of space-time. The extreme gravity of a black hole stretches the fabric of reality to its limits, allowing us to see hints of the underlying code. The way a black hole processes information, stores it, and potentially releases it through Hawking radiation is a masterclass in how the cosmic operating system functions under maximum stress. The clues we gather from these dark laboratories do more than solve a paradox. They guide us toward understanding the origin of the entire system, pointing back to the first moment of computation. Classical Big Bang presents a moment of infinite density, a singularity where all known laws of physics simply cease to apply. It is the ultimate dead end for our equations. But what if the universe never experienced this infinite breakdown? Loop quantum cosmology, an application of loop quantum gravity, paints a radically different picture of Genesis. It uses the discrete, granular nature of space-time to rewrite the origin story. Because space is quantized, woven from finite loops, it cannot be compressed into an infinitely dense point. There is a smallest possible size, a cosmic pixel. As the universe collapses back in time, it reaches this fundamental limit of density. Instead of collapsing into nothingness, immense quantum pressure acts like a cosmic spring, causing the universe to rebound. This is the Big Bounce, a transition from a previous era of contraction into our current era of expansion. The Big Bang was not the beginning of time, but a pivotal phase change in an eternal cycle. The quantum fabric, the operating system itself, has likely always existed, cycling through endless iterations of expansion and contraction. This model completely sidesteps the troubling singularity, replacing a mathematical absurdity with a physical, quantized process. Our universe's birth was not a mysterious explosion from nothing, but a grand rebound from a prior state. This transforms the Big Bang from a singular creation event into a mere transition within a much grander, perhaps timeless, cosmic process. It is the operating system rebooting, starting a new computational cycle. The clues to this profound bounce are not lost to the distant past. They might be imprinted on the oldest light in the cosmos, waiting for our telescopes to read the code. The hunt for the quantum fabric is a search for the universe's smallest possible signature. While we cannot see this granular structure directly, its subtle effects might ripple across the cosmos, leaving faint traces for our most sensitive instruments to find. The fundamental scale of this graininess is almost impossibly tiny, a distance known as the Planck length. To visualize this, if an atom were expanded to the size of our entire observable universe, a single Planck length would only be as tall as a tree. Probing something so minute requires extraordinary ingenuity. One promising method looks to the stars, using nature's most violent explosions as a laboratory. When a massive star collapses in a gamma-ray burst, it sends a tremendous flash of light racing across the universe for billions of years. If space is truly a digital pixel grid, then higher energy photons, those with more punch, might interact with this granular structure differently than lower energy ones. They could be slowed down by a minuscule amount, a phenomenon called vacuum dispersion. By comparing the arrival times of different gamma-ray energies from these ancient explosions, scientists are searching for a telltale lag, a signature that light does not travel through a perfectly smooth vacuum. Another approach listens to the faint echo of creation itself. The cosmic microwave background is the afterglow of the Big Bang, a snapshot of the infant universe. Theorists suggest that the violent quantum fluctuations of space-time in that first fleeting moment would have left a unique statistical fingerprint on this radiation. By meticulously mapping the subtle patterns in this ancient light with telescopes like the Planck satellite, cosmologists are hunting for the imprint of quantum gravity, a whisper from the universe's first moments when its underlying code was being written. Even our detection of gravitational waves opens a new window. As observatories like LIGO become ever more sensitive, they might one day detect a faint background hiss, the constant fizz and pop of the quantum foam. The collective churning of these microscopic space-time bubbles could create a stochastic signal, a murky noise beneath the clear chirps of colliding black holes, revealing the turbulent nature of the fabric itself. These experiments represent a beautiful partnership between deep thought and advanced technology, where abstract theory meets the precise language of measurement. The entire endeavor forces us to confront a staggering possibility. If this quantum fabric is real, and if it operates on an informational code, then the universe is not just described by mathematics, it is mathematics in motion. The cosmos could be running on a quantum processor. If the fundamental layer of reality is an informational fabric, then the universe is not just like a computer, it might literally be one, perpetually calculating its own existence. Pioneering thinkers like Seth Lloyd have championed this view, known as pancomputationalism. In this framework, the quantum fields that permeate everything are the physical hardware. The ceaseless, probabilistic dancing of particles represents the raw data processing, and the unbreakable laws of physics, from gravity to electromagnetism, are the elegant algorithms being executed. Every interaction, from the fusion of atoms in a star to the firing of a neuron in your brain, is a step in this cosmic computation. The universe is not merely described by mathematics, it is engaged in a continuous, universe-sized calculation, and the evolving output of that calculation is the reality we perceive and inhabit. The bits of this cosmic computer are not the simple zeros and ones of a classical machine. They are quantum bits or qubits. A classical bit is like a standard light switch, either definitively on or off. A qubit, however, is more like a dimmer switch that can be in a superposition of both on and off simultaneously. It holds multiple potential states at once, and its actual value only resolves when measured. This quantum parallelism allows a cosmic-scale quantum computer to process an astronomical number of possibilities concurrently. The evolution of these qubits over time forms immense quantum circuits. A particle's path through a magnetic field, or the entanglement of two photons across a galaxy, are not just physical events. They are operations in a circuit of unimaginable complexity, a sequence of logical gates manipulating quantum information on a cosmological scale. This perspective transforms our understanding of existence. It provides more than a powerful metaphor. It offers a concrete mathematical framework to describe the universe's dynamics. But it also forces a profound philosophical question. If the universe is computing, what is the ultimate answer it is trying to find? What is the cosmic program running? The purpose of this grand computation might be the most elusive code of all. Our most intimate experience of reality is a lie. The solid ground beneath your feet, the vast emptiness of the night sky, the steady forward march of time, these are not the bedrock of existence. They are the user interface, a grand and convincing illusion projected from a deeper quantum code. If space and time are emergent, then the continuous, flowing world we perceive is a masterful trick, akin to the illusion of motion in a film. A movie is just a rapid sequence of static images, yet our brain stitches them into a seamless narrative. Our entire reality could be a similar construct, a cosmic film projected from a quantum substrate that operates in a realm beyond space and time as we know them. This directly challenges our core intuitions about causality, the idea that one event must always follow another in a strict, linear sequence. In a fundamental quantum network, where every node is connected to every other through entanglement, the very concept of before and after might lose its absolute meaning. The flow of time could be a thermodynamic artifact, a consequence of the increasing disorder in the universe, not a fundamental river we are all floating on. These ideas resonate with ancient philosophical struggles. We are like the prisoners in Plato's cave, chained and watching shadows dance on the wall, mistaking those flickering images for the entirety of reality. The quantum fabric is the fire casting the shadows, a deeper truth we are only now beginning to perceive. This forces upon us the most unsettling questions. What is real? Is the chair you are sitting on truly solid, or is its solidity a collective behavior of quantum information? Is time itself real, or is it simply the way we experience the universe's memory of quantum correlations? And where does human free will fit into a cosmos that might be governed by deterministic or probabilistic quantum algorithms? Are our choices our own, or are we simply executing a line of code in a cosmic program that has been running for 14 billion years? These are not idle philosophical musings. They are the direct, inevitable consequences of taking our best physical theories seriously. The quantum fabric hypothesis blurs the line between physics and metaphysics, forcing a new dialogue about the nature of being itself. It suggests that understanding the universe is not just about cataloging its contents, but about cracking its source code, a journey that compels us to ask what we could possibly build once we learn to read it. The universe's source code is not just a mystery to be solved, but a toolkit to be opened. Decoding the quantum fabric could grant us capabilities that seem like magic today, rooted in the profound manipulation of reality itself. One of the most tantalizing prospects is new energy. If we understand how mass and energy warp space-time, could we learn to generate power by smoothing out quantum fluctuations in the vacuum, tapping into the endless churn of virtual particles popping in and out of existence? This zero-point energy, a faint hum in the empty void, might one day be a reservoir, even more revolutionary is the potential for propulsion. A warp drive, long confined to science fiction, is a theoretical concept grounded in general relativity. It would not push a ship through space, but contract the space in front of it and expand the space behind, riding a wave in the fabric itself. To build such an engine, we would need to engineer the quantum vacuum, controlling the very properties of space-time that we now believe are emergent. This is not about building a faster rocket, but about learning to steer the cosmic stage. While these grand visions stretch our imagination, a more immediate revolution is already unfolding in laboratories around the world. Our growing grasp of quantum information is directly fueling the development of quantum computers. These machines do not just calculate faster, they calculate differently, harnessing superposition and entanglement to solve problems that would take classical computers the age of the universe to crack. We are learning to speak the language of the cosmos, one qubit at a time. This journey leads to a staggering ultimate goal. If the universe is indeed a quantum computer, then understanding its fundamental programming language could allow us to rewrite small pieces of it. We could manipulate matter and energy with unimaginable precision, curing diseases by correcting quantum errors in biological molecules, or constructing materials with properties engineered from the ground up. The long-term vision is to move from observing the laws of physics to locally programming them, yet this immense power is matched by profound challenges. The energy scales needed to manipulate space-time directly are astronomical, far beyond our current reach. The decoherence that plagues quantum computers, where their fragile states collapse, is a constant reminder of how difficult it is to maintain quantum coherence outside of carefully controlled isolation. And the ethical questions are as vast as the cosmos itself. Who gets to hold the keys to reality's code? The path to harnessing the quantum fabric is long, but every step reveals a little more of the universe's magnificent architecture. Our most ambitious theories crash against the hard shores of experimental reality. The fundamental challenge is a simple, yet profound, gap in scale. The quantum grain of space-time is thought to exist at the Planck length, a size so minuscule that our most powerful particle colliders are like trying to probe a single atom with planet-sized tools. We simply cannot build a machine energetic enough to peer directly into this domain. This leaves brilliant frameworks like string theory and loop quantum gravity in a difficult position. They are magnificent mathematical castles, built with internal consistency and profound beauty, but we cannot yet send an expedition to see if their foundations touch solid ground. This lack of direct experimental data means that for now, these theories remain in the realm of profound speculation. They make predictions, but those predictions are often for energies or scales so far beyond our reach that we cannot design a test to confirm or refute them. This leads to a deeper philosophical debate. If a theory, by its very nature, proposes entities or dimensions that are permanently beyond any possible observation, can it still be considered science? This is the critique often leveled at the multiverse concept in string theory, where our universe is just one bubble in an infinite, bubbling foam of others. The idea is compelling, but if we can never interact with or detect these other universes, does the hypothesis move from physics into metaphysics? This is not just a minor hurdle, it is a fundamental challenge to the scientific method itself. Another profound puzzle is the problem of time. In our everyday world and in all of classical physics, time is a relentless, flowing river. But when we look at the fundamental equations of quantum gravity, something bizarre happens. The variable for time often vanishes completely. In this deepest description of reality, there seems to be no past, present, or future, only a vast, frozen network of correlations. The flow of time, our most visceral experience of existence, appears to be an illusion that emerges only when you have a large, complex system with a definite direction of increasing disorder. At the fundamental level, the universe might be timeless. These limitations can feel disheartening, but they are not a sign of failure. They are the signature of a frontier. Every great expansion of human understanding has begun with a period of confusion, where old tools break and new languages must be invented. The very existence of these profound problems is a beacon, calling for a new kind of physics, a new kind of mathematics, and a new generation of thinkers willing to question the very framework of our questions. This honest acknowledgement of our current limits is what fuels the search for simpler, more testable alternatives that might yet illuminate the dark. The smooth stage of space-time might be an elegant approximation, but the deeper code could be written in the language of pure cause and effect. Causal Set Theory offers a radically minimalist vision for this underlying reality. It proposes that the fundamental substance of the universe is not space or time, but a vast collection of discrete events, like points on an unimaginably vast sheet of paper. What truly matters are the causal connections between them. One event either influences another or it does not. This simple, binary relationship of before and after is the only primary ingredient. From the sheer number of these events and the intricate web of their causal order, the smooth, continuous illusions of four-dimensional space and time are somehow woven. The fabric of reality is not a fabric at all, but a cosmic list of cause and effect pairs, a story written solely in the language of what leads to what. A completely different computational approach is unfolding in Stephen Wolfram's physics project. This initiative models the universe not with complex equations, but as a hypergraph, a network where connections can link any number of points. The fundamental rule is simple, a set of instructions for how this hypergraph rewrites itself over and over. From this relentless, automated process of transformation, the familiar laws of physics, particles, and even space itself are meant to emerge as large-scale patterns. It is the universe as a cellular automaton, where simple rules generate breathtaking complexity, suggesting our physical laws are not fundamental, but are the emergent habits of a system computing itself into existence. Other paths, like non-commutative geometry, propose that at the tiniest scales, the very concept of a point in space becomes fuzzy and ill-defined. In this mathematical landscape, the order in which you measure things matters profoundly, leading to a geometry where uncertainty is built into the fabric of location itself. Each of these models is a different candidate for the universe's programming language. Causal Set Theory writes its code in the logic of causality. The Wolfram project uses the language of simple computational rules. Each dialect has its own elegance and its own unresolved challenges, its own way of generating the world we see from a set of deeper, more primitive axioms. This rich diversity of thought is not a sign of confusion, but the great strength of theoretical physics. It is a chorus of different voices all trying to sing the same fundamental song, each revealing a different facet of a truth that is larger than any single framework. This collective effort inevitably circles back to us, the observers. If reality is a computation or a causal network, then what is the role of the mind that perceives it? Does our consciousness simply read the cosmic output, or could it be a more integral part of the processing itself? A quantum particle exists as a cloud of potential until you look at it. This simple, bizarre fact places the observer at the very heart of the quantum mystery. In the traditional Copenhagen interpretation, the act of measurement is what forces this cloud of possibilities to choose a single, definite state. The wave function, a mathematical description of all possible outcomes, collapses into one reality. This process has long begged a profound question. What is so special about measurement? Is it the physical interaction of a detector, or could it be the awareness of a conscious mind that finalizes reality? Physicist Eugene Wigner famously explored this with a thought experiment. He imagined a friend in a lab performing a quantum measurement. For the friend, the outcome is definite. But for Wigner outside the room, until he asks for the result, the entire system, including his friend's mind, remains in a blurry superposition of having seen all possible outcomes. It suggests that only a final act of conscious awareness resolves the situation. This line of thinking points toward a participatory universe, where consciousness is not a passive spectator, but an active player in weaving the fabric of reality. In the context of the quantum fabric, this raises a staggering possibility. If space and time emerge from a network of quantum relations, could conscious observation be the process that stitches these relations into a stable, classical world? Perhaps the continuous reality we experience does not just run in the background, but is crystallized moment by moment through our interaction with it. The universe's operating system might require a user to boot up its display. Most physicists today strongly favor a materialist explanation. They argue that collapse is caused by decoherence, a physical process where a quantum system interacts with its messy environment, effectively erasing its delicate superpositions. In this view, consciousness is an emergent property of complex neural computation, a beautiful and intricate outcome of the physics, not its cause. The measurement is complete long before any awareness occurs. Yet the hard problem of consciousness remains. Why should any physical process, no matter how complex, give rise to subjective experience at all? This is the chasm between the objective description of brain states and the inner feeling of what it is like to be you. The mystery of quantum measurement and the mystery of consciousness seem to brush against each other in the dark, leaving room for speculation that they might be deeply connected. This topic sits at the precarious boundary between science and philosophy. It challenges the limits of physical explanation, forcing us to ask if a complete theory of the universe can ever exist without accounting for the minds that perceive it. If consciousness is indeed fundamental to the cosmic code, then the ultimate fate of the universe might not be a predetermined script. It could be a story still being written with our observation as part of the ink. Time feels like a river flowing in only one direction. You can remember the past, but you cannot remember the future. This one-way street of existence is what physicists call the arrow of time, and its origin is one of the deepest mysteries in the cosmos. Strangely, the fundamental laws of physics, from Newton to quantum mechanics, are almost entirely time-symmetric. They work just as well running forward as they do in reverse. A video of two planets orbiting each other would look perfectly normal played backwards, but a video of a shattered cup reassembling itself on a table would look absurd. Why is that? The answer lies not in the laws of motion, but in a concept called entropy. Entropy is a measure of disorder, and the second law of thermodynamics states that the total entropy of an isolated system always increases over time. It is the reason heat flows from hot to cold, why perfume diffuses in a room, and why your desk tends to get messier, not tidier, unless you expend energy to clean it. The arrow of time is the arrow of increasing disorder, but this just pushes the mystery one step back. Why was the entropy of the universe so incredibly low in the first place? The Big Bang presents a monumental puzzle. The early universe was a state of exquisite order, a hot, dense, and remarkably uniform soup. This was a low-entropy configuration, a tightly wound spring that has been uncoiling ever since, driving the cosmic expansion and the flow of time itself. Our entire experience of past, present, and future seems to depend on this single initial condition. So what set that cosmic spring in the first place? The quantum fabric might hold the key. In a timeless, fundamental quantum network, there is no past or future, only a vast web of correlations. The flow of time we perceive could be an emergent property of quantum decoherence, the process by which quantum systems interact with their environment and lose their fuzzy superpositions, settling into the definite states of classical reality. Every quantum measurement that resolves a possibility into a fact is a tiny tick of the cosmic clock, and the relentless increase of these correlations and their associated disorder is what we experience as the passage of time. Some theories, like the quantum bounce, offer a compelling picture. If our universe was born from the collapse of a previous cosmic era, that collapse could have naturally reset the entropy to a low state, providing the clean slate needed for time's arrow to begin anew. Our universe's history, from the Big Bang to the distant future, might be just one cycle in an eternal process of cosmic renewal, where time's flow is rebooted with every bounce. Understanding this is critical for decoding the universe's operating system. It reveals that the progression of events is not a fundamental feature of the code, but a high-level program that runs because of a specific, low-entropy initial state. Time is not in the processor's hardware, it is in the data. This investigation into the very nature of temporal flow forces us to lift our gaze from the quantum realm to the grandest scales of all, to ask how the overall structure of the cosmos informs its ultimate destiny. The grand cosmic web is the largest pattern in existence, stretching across billions of light years. It is a delicate lace of galaxies strung along invisible filaments of dark matter, with immense, empty voids between them. This is the universe's ultimate large-scale structure, a majestic architecture that seems impossibly vast, yet its blueprints were drawn in the first fleeting moments of reality, on a scale trillions of times smaller than an atom. The source of this cosmic design was quantum noise, the inherent jitter and fuzziness of the quantum fabric itself. In the instance after the Big Bang, the universe underwent a period of hyper-fast expansion known as cosmic inflation. During this explosive stretching, the vacuum of space was not perfectly smooth and silent. It was a seething sea of quantum fluctuations, tiny, random variations in energy, dictated by the rules of quantum uncertainty, were flickering in and out of existence. As the universe inflated at a staggering rate, these microscopic ripples in the quantum field were stretched along with it, magnified from the quantum realm to the cosmic scale. Imagine the surface of a balloon as you begin to inflate it. If you draw a tiny, wiggly line on it with a fine-tipped pen, that line will expand and grow into a large, sweeping curve as the balloon swells. Cosmic inflation did exactly this, but with quantum wrinkles. These amplified ripples became slight differences in density, tiny hills and valleys in the otherwise uniform distribution of matter and energy. Gravity then took over. Over hundreds of millions of years, gravity pulled matter toward these slightly denser regions. The hills grew into mountains and the valleys deepened into voids. The dark matter formed an invisible skeleton, and ordinary matter, the gas and dust that would become stars and galaxies, flowed along this scaffold, condensing into the glittering nodes and filaments we see today. Every galaxy cluster, every vast empty desert of intergalactic space, can trace its lineage back to a random quantum tremor in the newborn universe. This is the most profound connection imaginable. The same quantum rules that govern the behavior of a single electron also orchestrated the formation of the entire cosmic web. The universe's operating system took a random seed, a single bit of quantum information, and ran a gravity-driven algorithm for billions of years to produce a galaxy. This forces us to look at the vacuum of space in a completely new light. It is not an empty nothingness. It is a quantum substrate brimming with potential, whose faintest whispers become the grandest structures in reality. This deep unity, from the quantum pixel to the galactic supercluster, suggests that the cosmos is a single, coherent computation, one where the very nature of emptiness holds the key to everything. The silence of empty space is a cosmic illusion. What we perceive as a perfect void is actually a vibrant, energetic medium known as the quantum vacuum. Far from being nothing, it is the lowest energy state of the quantum fabric, a seething sea of potential. Due to the fundamental uncertainty of quantum mechanics, pairs of virtual particles and their antiparticles constantly flicker into existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and vanishing. This endless, frothing dance of creation and destruction is not just theoretical. We can observe its effects in a laboratory through a remarkable phenomenon called the Casimir effect. When two perfectly smooth, uncharged metal plates are brought extremely close together in a vacuum, they are pushed together by a mysterious, invisible force. The reason is that the gap between the plates is so narrow it restricts the kinds of virtual particles that can pop into existence there. Outside the plates, a limitless variety of fluctuations can occur, but inside the narrow gap, only certain wavelengths are permitted. With more activity pushing on the plates from the outside than from the inside, the net result is a measurable force that pushes the plates together. This is not magic, it is direct experimental evidence that so-called empty space is alive with quantum activity. This vacuum energy is not just a curious side effect, it is the central character in the universe's greatest drama. We now know this energy, often called dark energy, is responsible for the accelerated expansion of the cosmos. It is as if the quantum vacuum itself possesses a kind of negative pressure, an inherent springiness that causes space itself to stretch at an ever-increasing rate. This makes the quantum vacuum the true engine of cosmic evolution, the dynamic stage upon which all of existence plays out. Yet this revelation comes with a staggering puzzle, the cosmological constant problem. When physicists try to calculate the theoretical energy density of the quantum vacuum based on the sum of all these particle fluctuations, the result is a number so astronomically large it should have torn the universe apart an instant after the Big Bang. The observed value of dark energy, however, is almost zero, a number 120 orders of magnitude smaller. This is the most embarrassing and profound discrepancy in all of physics, a glaring sign that we are missing something fundamental about how the quantum vacuum truly operates. Unlocking this mystery is the key to understanding not just the origin of the cosmos, but its ultimate fate, forcing us to ask how this dynamic vacuum will shape the final state of all that exists. The universe's final state appears to be a cold, dark, and eternal silence. This is the heat death, the ultimate victory of entropy, where every star has burned out, every black hole has evaporated, and the cosmos becomes a uniform, lukewarm sea of diluted particles. There is no more energy to extract, no more work to be done. The cosmic computation grinds to a halt, having reached its state of maximum disorder. Yet this bleak picture, born of classical thermodynamics, might be incomplete. The quantum fabric beneath space-time could have a final, surprising instruction in its code. If the universe is a quantum system, then nothing is ever truly static. Even in this vast, dark equilibrium, quantum uncertainty would persist. The vacuum would still fizz with virtual fluctuations, and given an eternity to play out, a rare quantum tunneling event could occur. A random fluctuation in the quantum field might suddenly gather enough energy to spark a new inflationary bubble, a baby universe budding off from the cold corpse of our own. This new cosmos would inflate rapidly, creating its own space, time, and matter, completely disconnected from our history. It would be a spontaneous rebirth from the quantum vacuum, a new program booting up from the dormant hardware of the old. An even more profound vision comes from Roger Penrose's conformal cyclic cosmology. He proposes that our universe is not the first, nor will it be the last in an infinite series. In the far, far future, when all matter has decayed into light and the universe expands into a featureless void, it loses any sense of scale. At this point, its end state becomes mathematically identical to the hot, dense, and similarly featureless beginning of a new Big Bang. The universe effectively forgets how big it is, and the end of one eon seamlessly becomes the beginning of the next in a cyclic process he calls an eon. It is not a violent crunch and bounce, but a smooth, geometric transition where the universe resets its own clock. In this model, the quantum fabric is eternal, its fundamental code persisting through each rebirth, while the content of reality, the particles and forces, are reconfigured anew. These are not just philosophical speculations, they are testable scientific ideas. Penrose suggests that the violent collisions of supermassive black holes from a previous eon might have left faint, circular imprints in the cosmic microwave background, concentric rings of polarized light that we could potentially detect. Finding such a signal would be direct evidence that our universe is just one chapter in an infinite book. This long-term perspective transforms our understanding of existence. The cosmic operating system appears to be built for eternity, not for a single, finite run. The heat death is not an absolute end, but a phase change, a return to a blank slate from which new possibilities can quantum mechanically emerge. This vision of a cyclic or rebirthing cosmos completes a profound unity, connecting the fate of the universe directly back to its quantum origins. This relentless quest for a final theory is the human mind reaching for the cosmos's ultimate blueprint. A theory of everything represents the pinnacle of this journey, a single, elegant framework capable of describing every force and particle in the universe under one roof. It aims to weave together the four fundamental forces: gravity, which sculpts the cosmos; electromagnetism, which binds atoms and gives us light; and the strong and weak nuclear forces that govern the atomic nucleus. The quantum fabric is the proposed bedrock for this grand unification. Whether it manifests as the vibrating strings of M-theory or the woven loops of a complete loop quantum gravity, the goal is identical: to uncover the universe's master algorithm. This is not merely about tidying up our physics textbooks. It is about discovering the source code that generates reality itself, from the birth of a galaxy to the quantum spin of an electron. Such a theory would be the final key, allowing us to read the universe's operating system without any missing lines. The pursuit itself is a testament to an unyielding human drive to comprehend existence in its totality. We are not content with a collection of separate rules for large and small phenomena. We crave a single, coherent story. Achieving this unification would be a monumental milestone, arguably the greatest intellectual achievement in history. It would not, however, be an end. Like any profound discovery, it would immediately open new and deeper mysteries. Understanding the code is one thing. Understanding why this particular code was written and what it is ultimately computing would become the next great frontier of inquiry. The equations of physics are not just descriptions, they are the reality. To read the universe's source code, you must become fluent in the language it is written in, a dialect of advanced mathematics that describes shapes, spaces, and symmetries beyond our everyday perception. The smooth, curving landscape of general relativity is mapped using differential geometry, a mathematical framework that can handle bends and warps in space-time. This is the language of the cosmic stage, but when we descend to the quantum level, we need a new vocabulary. The probabilistic, granular world of the quantum requires the tools of algebra and topology, which deal with discrete structures and the properties of spaces that remain unchanged even when they are stretched or twisted. These two mathematical worlds, the continuous and the discrete, must somehow merge to describe the quantum fabric. In loop quantum gravity, this fusion is stunningly visualized. The spin networks that represent quantized space are rooted in graph theory, which studies networks of connected points, and group theory, the mathematics of symmetry. Each line and node in this cosmic graph is not just a drawing. It is a precise mathematical object representing a quantum of area or volume, with its properties dictated by the rules of symmetry. String theory takes a different but equally beautiful path. It proposes that the extra dimensions required for its math are curled into intricate, complex shapes known as Calabi-Yau manifolds. These are not simple spheres or donuts, but multi-dimensional shapes with very specific topological properties that determine the number and types of particles in our universe. The vibrational note of a string, and thus the particle it becomes, is dictated by the exact geometric form of this hidden, compactified space. Why do physicists trust these incredibly abstract mathematical guides? Because throughout history, the elegance and self-consistency of a mathematical framework has often been a beacon, pointing toward physical truth long before any experimental confirmation. The power of a beautiful equation to predict reality is itself a profound clue. It suggests that the universe's operating system is not just described by mathematics, but that it is a mathematical structure. The laws of physics are the immutable logic of this structure, and the unfolding cosmos is a magnificent calculation in progress. This deep connection between abstract math and concrete reality forces us to confront a truly fundamental question about the nature of existence itself. Are the laws of physics the universe's ultimate constitution, or are they merely local ordinances? This question cuts to the very core of our quest. On one side of this profound debate, physicists like Sean Carroll propose a vision of fundamental laws. In this view, the mathematical rules governing forces like gravity and electromagnetism are not emergent. They are the bedrock, eternally etched into the fabric of reality. They exist in a vast, abstract realm of possibilities known as a configuration space, a cosmic library containing every possible state of the universe. The path our reality takes is simply one specific volume pulled from these stacks, its trajectory dictated by these immutable, fundamental commands. This perspective is powerful and intuitive, suggesting the operating system runs on a fixed, unchangeable code. Yet, a competing and equally compelling idea suggests the opposite. Perhaps the laws themselves are not fundamental at all, but rather collective phenomena that emerge from the chaos of the quantum fabric. Consider the second law of thermodynamics, the law that dictates the inevitable increase of disorder, the very arrow of time itself. This law feels absolute in our daily lives, but it is not a fundamental decree. It emerges from statistics, from the simple, overwhelming probability that a system with many moving parts will tend toward greater chaos rather than spontaneous order. A single air molecule in a room follows the fundamental laws of motion, but it has no temperature or pressure. These properties only manifest when you have a vast ensemble of molecules, their collective behavior giving rise to entirely new, emergent laws. So, could gravity itself be such a phenomenon? In the quantum fabric paradigm, the laws we hold sacred might be effective laws. They are the large-scale, stable patterns that arise from the ceaseless, dynamic interactions of the underlying network. Think of a flowing river. We can describe its current with elegant equations, but those equations are not fundamental to the water molecules themselves. They emerge from countless molecular collisions, the pull of gravity, and the friction of the riverbed. The smooth, continuous law of the river's flow is a high-level description of a chaotic, discrete underlying reality. If this emergent view is correct, then the true fundamentals of the universe might be far simpler and more abstract than the complex laws we've discovered. They could be basic principles of information processing, logic, or geometry. The cosmic operating system would not be a rigid set of rules, but a dynamic, evolving process, a computation that generates its own laws as it runs. This debate fundamentally reshapes the search for a theory of everything. Are we hunting for the universe's final, fundamental list of commands, or are we trying to understand the simple, initial algorithm that generates all the complexity we see? The answer to this riddle may be hidden in a concept of breathtaking beauty, the role of symmetry in shaping reality itself. Symmetry is the silent architect of reality. The universe does not play favorites with location or direction. Its laws remain unchanged whether you are here, there, or anywhere else. This profound principle of invariance is the hidden blueprint behind everything. The equations governing particles and forces exhibit deep symmetries, remaining consistent under transformations like rotation, translation through space, or even the reversal of time. The entire standard model of particle physics is constructed upon a framework of gauge symmetries, which are like internal, invisible dials that can be turned without altering the fundamental physics. Yet, if these symmetries were perfectly preserved, our universe would be a vastly different and much simpler place. All particles would be massless, zipping around at the speed of light, and the rich diversity of matter we see would not exist. The cosmos as we know it emerges not from perfect symmetry, but from its breaking. The most famous example is the Higgs mechanism. In the early, hot universe, a quantum field now known as the Higgs field possessed a perfect symmetry. As the cosmos cooled, this symmetry broke like water freezing into ice crystals. This phase transition gave mass to fundamental particles, slowing some down to form the atoms that build our world. This is not a minor detail, it is the creative act that allowed complexity to arise from simplicity. In the context of the quantum fabric, these phenomena take on a deeper meaning. The fundamental symmetries of the underlying network, the spin foam or the string vibrations, are likely perfect and pristine. The symmetries we observe in our four-dimensional space-time, like the consistency of physical laws everywhere, are then emergent properties. They are the large-scale, stable patterns that arise from the collective behavior of the quantum substrate. Much like the overall hexagonal symmetry of a honeycomb emerges from the collective behavior of countless bees, even though no single bee is enforcing the pattern. This understanding transforms the search for a unified theory. It becomes a hunt for the ultimate, unbroken symmetry of the quantum fabric, a single, elegant mathematical principle from which all forces and particles are derived as broken fragments. Grasping this is like moving from reading individual lines of code to comprehending the entire programming language's core logic. It prepares us for the final, most profound question of all, one that asks not just how the system runs, but why it exists in the first place. The quantum code might be running more than one universe. Our reality could be a single thread in an impossibly vast tapestry of parallel existences, a concept that emerges naturally from the deepest layers of our theories. The most famous version of this idea comes from the many worlds interpretation of quantum mechanics. It proposes that every time a quantum system faces a choice, like an electron deciding which path to take, the universe does not merely pick one outcome. Instead, it splits, branching into multiple, equally real worlds where every possible result actually happens. In one branch, the electron goes left, in another it goes right, and both histories unfold from that point forward, completely separate and unaware of each other. This is not a chaotic multiplication of matter, but a splitting of the wave function itself, where every possibility encoded in the quantum state is realized in its own branching timeline. The universe's operating system does not delete the unused code. It simply forks the process, running every possible version of the script simultaneously. String theory adds another dimension to this cosmic proliferation. Its mathematical framework reveals a staggering landscape of possible vacuum states, each with different properties for the fundamental constants and forces. Our universe, with its specific values for the strength of gravity or the mass of an electron, might simply be one valley in this vast cosmic terrain. Other universes with radically different physics could exist in other valleys, each one a separate bubble in an eternally inflating multiverse. In this view, the Big Bang was not a unique event, but one of countless spontaneous nucleation events in an eternal meta-universe. The implications are staggering. If true, our laws of physics are not special or fine-tuned. They are merely local bylaws, the random outcome of which bubble we happen to inhabit in an infinite cosmic foam. The profound constants that make our life possible are not a cosmic coincidence, but a selection effect. We exist in this particular universe because its laws permit our existence, a concept known as the Anthropic Principle. While these ideas are compelling, they remain deeply controversial because they are currently, and perhaps permanently, untestable. How can we ever observe a universe from which we are causally disconnected? This pushes the multiverse hypothesis to the very boundary of science, challenging the requirement that a theory must be falsifiable. Yet, it represents the ultimate scaling of the quantum fabric concept. If reality is a computational substrate, then the multiverse is the ultimate expression of its processing power, a cosmic computer running countless simulations in parallel. This expansive vision forces a humbling perspective. Our entire cosmos, with its hundreds of billions of galaxies, might be just one instance of a code running on a system of unimaginable scale. It brings us back to the most human of questions, not about the machinery of the cosmos, but about our place within its potentially infinite iterations. Our lives feel rich with purpose and emotion, yet they may arise from a system of pure information. This idea can seem cold, as if our deepest loves and struggles are mere lines in a cosmic program. But this perspective holds a different, more profound kind of magic. We are not just passive outputs of this computation, we are the process becoming aware of itself. Our consciousness is likely an emergent phenomenon, a stunningly complex pattern woven from the very quantum computations that orchestrate the cosmos. We are the universe's way of looking back at its own code, of questioning its own nature. This is a thread that connects the most ancient human intuitions to our most modern science. For millennia, spiritual traditions have spoken of a fundamental oneness, a universal web where everything is interconnected. Today, physics points toward the same truth through the language of quantum entanglement and relational networks. We are not isolated observers, but deeply embedded nodes in this cosmic web, our very thoughts and perceptions shaped by its intricate connections. The quantum fabric does not erase meaning, it recontextualizes it. Our search for purpose is not a futile rebellion against a meaningless machine. It is the system's own inherent drive toward self-understanding unfolding within us. Your moment of awe under a starry sky, your flash of insight, your feeling of connection to another person, these are not illusions. They are the human-scale experience of the cosmos computing its own existence, and we are active participants in that grand endeavor. This realization carries a deep responsibility. If we are truly part of a self-aware cosmic system, then our actions, our curiosity, and our care for this world matter on a fundamental level. We are not just reading the universe's source code, we are helping to write its next chapter through every question we ask and every discovery we make. Reality seems to be woven from three fundamental threads. The first is a granular quantum fabric, a dynamic substrate from which the smooth illusions of space and time crystallize. The second is information, the fundamental it from bit that constitutes the raw material of existence. The third is connection, the relational network of entanglement that binds everything into a coherent whole. Loop quantum gravity paints this with spin networks and foams, a universe stitched from discrete loops of gravity. String theory composes it with vibrating strands dancing in hidden dimensions. Though their mathematical languages differ, they harmonize on a core theme. Our classical reality is a grand emergence. The forces we consider fundamental, from gravity to electromagnetism, are not the bedrock. They are the elegant software, the stable algorithms that run on this deeper quantum hardware. Black holes are not cosmic dead ends but the ultimate data storage devices, their event horizons encoding a universe's worth of information in a shimmering two-dimensional skin. The early universe, in its first quantum whisper, used the jitter of the vacuum to seed the entire cosmic web of galaxies. This vision synthesizes into a single, staggering possibility. The cosmos is not merely like a computer, it is a vast, ongoing quantum computation. Every interaction, from a photon striking your eye to a star collapsing into a black hole, is a step in this cosmic calculation. The physical laws we work so hard to uncover are not decrees etched in stone. They are the emergent, reliable habits of a system processing an unimaginable amount of information. This coherent picture does not answer every question. Instead, it reframes our very pursuit of knowledge. We are no longer just astronomers or physicists cataloging the contents of the stage. We are cosmic programmers slowly learning to read the source code of the stage itself. This new way of seeing reality as a dynamic, interconnected, and computationally rich process is the true treasure of our exploration. It sets the stage for one final, humbling look at our own place within this magnificent code. This journey to the edge of understanding has redefined the very ground beneath our feet and the time that carries us forward. We have traced the contours of a cosmos where space and time are not the foundation, but a magnificent and convincing illusion emerging from a deeper quantum reality. The intricate loops and spin networks of loop quantum gravity, the elegant vibrations in hidden dimensions from string theory, and the mind-bending holographic principle all paint different facets of the same profound truth. They are competing visions of the universe's ultimate operating system, a source code written in a language we are only beginning to decipher. While these frameworks remain incomplete, their very existence reshapes our place in the cosmos. We are no longer just actors on a cosmic stage, but participants in a dynamic, computational process, a universe that computes its own existence. The great mysteries of quantum gravity, the nature of time, and the origin of everything are not yet solved, but the pursuit itself is a testament to human curiosity. As the physicist Richard Feynman once noted, the universe is under no obligation to make sense to us, and yet here we are, persistently unraveling its secrets. This quest expands not only our knowledge but the very boundaries of our imagination. The exploration does not end here. I encourage you to keep questioning, to read further, and to share your own thoughts and wonder in the comments below. If this journey into the quantum fabric has sparked a new curiosity within you, please subscribe for more deep dives into the profound mysteries of our cosmos. Thank you for joining me on this incredible exploration of reality's deepest layer.